Hello everyone, welcome to Weekly Physics in CSZC. Together with me, I'm Sir Daniel Hernandez, one of the physics instructors here in Grad School of Zamboanga City. Today we're going to talk about the first part of our lesson in electricity, particularly on electrostatics. Now, in this particular course, we're going to cover um, four major fields in classical physics. We will deal with electricity, we'll deal with magnetism, we'll deal with optics, and of course, introductions to modern physics concepts. But first is we want to identify what is really happening when we talk about electricity. And we want to understand what is the nature of electricity, how does electricity work, and where does it come from. Before understanding those lessons, those ideas, we want to understand first static electricity. When we say static electricity, it is all about how electricity interact in the system when it is not moving. From the term static, not moving. So, what do we mean by electrostatics or static electricity, and how does it differ with electrodynamics or dynamic electricity? So, we'll explore those ideas later on. But first, we need to understand what do we mean by electricity. To further understand the term electricity, we need to define what it is. Electricity from is has its etymology from the Greek word elektros, meaning charge. Electricity is defined as the interaction of charged particles or charged materials. And remember, every object has particles, is made of atoms, and hence electricity is the interaction where inside every object in the universe has its own charged particles. In electricity, we understand or we deal with or we study the nature of electrons. Why electrons? Because only the electrons are located outside the nucleus of the atom. Remember, every object is made out of matter. And matter is anything that occupies space and has mass. Every object has subatomic particles. We have electrons, protons, and neutrons. Now, the protons and the neutrons are located inside the nucleus, while on the other hand, the electrons are located outside the nucleus. Hence, both of them is bonded with a nuclear energy, but the proton and the neutron has a very strong one. Protons cannot get out the nucleus, while electrons are free to interact with other electrons when they have the opportunity. Hence, electricity is all about studying electrons and how does electrons interact with other electrons. To further understand electricity, let's talk about charges. When there is an electric charge, we expect that there is electricity. But how does electricity co- is connected, or how is electricity connected with electric charge? An electric charge is a physical property of an object. Remember that object is a matter, and a matter is built out of atoms. So it has subatomic particles, and that particular property or physical property of a material is an electric charge. Since matter is made out of atoms and there are electrons, protons, and neutrons, so it has the ability to attract or repel a material. So if a matter has a physical property of any material that has a physical property of an electric charge, it has the ability or the capability to attract or repel a charged material or a charged object or a particle in that sense. Not just it has its own ability or capability to attract something, but it has also the same ability to be attracted to something or to be repelled by something. At the same time, that something should be a charged particle or a charged object. Now, we cannot attract or repel a charged particle with an, a non-charged particle or any object or any particle that is not charged. So let's deal with that later on. If an electric charge is a physical property of an object, then what particular objects do we need to consider? Now, there are two kinds of materials that we use in studying electricity. One is the metal, and the other one is the non-metal. So what are metals and what are non-metals? Of course, metals are solid objects primarily, and non-metals are not so solid, right? But in a manner of speaking, if we go back to our lessons in chemistry, we know that metals, okay, we know metals are materials that can easily lose electrons, while non-metals are materials that accepts electrons. This process is what we call ionization. In our lesson in chemistry, metals can be ionized and non-metals can be ionized also in the form of a cation and an anion. So how do we form a cation and an anion? A cation is a positively charged ion and an anion is a negatively charged ion. So which among the two, metals and non-metals, has an equivalent of an ionized particle? Is metal a cation or an anion? Are non-metals cation or an ion? So how do we classify a cation and an anion? And a cation is a positively charged material or ion, and an anion is a negatively charged ion. So how do we have a cation? Primarily, metals are cations. They turn into a cation because only the metals can lose electron. They lose electron, then they become positively charged. And how do they become a positively charged material? Remember that when a metal is going to bond, it needs to give off electrons. And remember that any element, any matter, has the same number of protons, electrons, and neutrons when it's in a stable manner or stable state. It doesn't necessarily be in a ground state, but it's stable. Say for example, sodium has magnesium rather. Let's take magnesium as our example. Magnesium has an atomic number of 12. Therefore, it tells us that there are 12 protons and electrons, and there are 12 neutrons. Electrons are negatively charged subatomic particles, and protons are positively charged subatomic particles, and neutrons doesn't have charge at all. That's why any atom in inertial state of reference, they don't have any charge at all because they have balanced distribution of charges. Now, when a metal loses electrons, so if magnesium loses electrons, so from 12 electrons it becomes it loses one electron. Then from 12 electrons there are only 11 electrons left. So which among the two subatomic particles is greater than one another? Of course, it's the protons. Protons, the total number of protons present in the system are 12 protons, and then there are 11 electrons, right? Now, protons has a positively charge, and electrons is a negatively charged. So who has the greater amount will carry the charge. So if magnesium loses an electron, it becomes a positively charged material or a particle because there are more protons in the system than the electrons, so thus becoming a positively charged ion, making it a cation. And that happens to metals. Non-metals, on the other hand, is that they are accepting electrons from the metals. And if they accept electrons, the number of electrons present in the system of the non-metals will increase. Saying chlorine. Chlorine has an atomic number of 17, so there are 17 electrons and 17 protons. If chlorine accepts electrons from, say for example, from magnesium, magnesium loses 1 electron and then chlorine will receive 1 electron from magnesium, thus making it a total number of 18 electrons and 17 protons. So, which among the two subatomic particles is greater than another? Has the highest number? Of course, electrons, there are 18 electrons and 17 protons. Hence, if there are 18 electrons and 17 protons, what will happen to the charge of the object? Since there are more electrons present in the system, thus making it a negatively charged particles and becoming an ion. So that happens to non-metals and to metals. So these two types of materials are the materials that we're going to use in studying electricity and magnetism. Of course, if there are metals and non-metals, we need to understand how does this metal and non-metals, or how do metals and non-metals being used in studying electricity to allow the flow of electric charges. Now, there are 3 kinds of materials or types of materials that we allow or that we use to allow the flow of electric charges. Having the flow of electric charges meaning having electricity at all. But if there is a flow of electric charge, then there is electricity running. But if there is no flow of electric charge in the system, then there is no electricity running at all. So we need these types of materials to allow the flow of electric charges. We have conductors, semiconductors, insulators, and of course, superconductors. Conductors are materials that allows us to have a good flow of electric charges. Primarily, conductors are metals. And we have insulators. These are materials that has a poor flow of electric charges. These are non-metals such as silicon, rubber, plastics, and so on and so forth. Conductors, one good example of conductors, we have copper, gold, silver, nichrome, magnesium, and so on and so forth. Semiconductors, this is a mixture of a conductor and an insulator that goes between 2 abilities. It has the ability to conduct electricity, and it has also the ability to insulate electricity. On the other hand, superconductors are materials that have zero resistance to conduct electricity at all. So, superconductors, this is the new trend in material sciences, in material physics. Superconductors are being studied where it is being used by high-powered objects that has a zero resistance to conduct electricity. Not all conductors has a zero resistance to conduct electricity. Of course, there are limits of conducting electricity. And we need these conductors to let electricity flow in our everyday objects. When the birth of computer, during the birth of computer, we use conductors. We don't use semiconductors. Semiconductors came in when we have already our laptops, cell phones, and so on and so forth. Right? And the birth of new technology. In the classical technology, we use conductors. The first computer is very big because we are using conductors. Imagine that the first IBM computer is the size of a building. Just for example, is the size of the building. That's the first computer. and that is only the server that allows computing. And so if you remember the Turing machine, the first computer that is used during World War II, if you notice, there are big wires, very thick wires, and all of it are made of metals. And those are conductors, very big ones. But at the birth of new technology, because using conductors would increase the cost of the material. Hence, if there is an increase in the cost of the raw material, also the selling price would increase. Now, manufacturers decided that we need to decrease the price of the raw material so that we can manufacture more items. Thus, scientists were able to invent semiconductors. Small material, small objects, but has the same ability to conduct electricity, a good conductor of electricity. At the same time, they are insulating or allowing a poor flow of electric charges. Now, there are many kinds of semiconductors present in our age right now, and one semester is not enough to discuss all about semiconductors. And that's how we deal with physics. Physics is revolutionary. As time passes by, we evolve from a bigger picture down to the smaller picture, and we continue to discover more things. Right? Now, these materials are very, very beneficial in studying electricity, conductors and insulators. Because without conductors, we cannot allow our appliances to run. Without conductors, our light bulbs will not emit light. Without conductors, our phone cannot charge. And without insulators, we would suffer from electric shock. Right? That's why every wiring system has a rubber coating to prevent the jumping of electric charges from the conductors. An insulator serves as a protective coating to these conductors so that we will be protected from the harm of electric charges. And now, having these three types of materials that we use in studying electricity, we always come into our mind, how do electric charges charge an object? How do we charge an object by means of increasing the amount of electric charges present in the system? How do we say it's a positively charged particle? How do we say it's a negatively charged object? And there are many ways on how to charge an object, and there are two famous methods of charging. This charging process is increasing the number of electrons in a certain material. This is not the same with the charging that we do in our phones, but this charging of materials would allow us to have a flow of electricity. Okay? Now, there are two kinds of charging process. The two famous ones. I'm going to discuss the famous ones. Conduction and induction. Conduction is a process of transferring electrons through binary contact, meaning two surfaces must be in contact with each other. So if there are two surfaces that are in contact with each other, there should be friction present. Remember, what friction is a force that allows two surfaces to be in contact with each other. And then what happens then if a charged material and another material that is not charged come into contact with one another? The electrons from the charged material will transfer to the other material. Thus, the other material, say it's a neutral charged particle, will gain electrons. So what will happen to them? What will happen during the transfer? The neutrally charged object or particle will become a charged particle or object by means of conduction. Induction is another type or a process of charging or transferring electrons. Induction is where we place a charged material near a neutrally charged object. And how do we do that? I have here a simulator that will show us how static electricity works, especially how do we do the process of charging by means of conduction and by induction. Now, there are three objects present in our simulator. We have a wall, a balloon, and a sweater. Now, notice that all of the objects contain subatomic particles such as protons and neutrons. The protons are represented by a positive charge, and the electrons rather are represented by a negative charge. Now, first is we need to demonstrate. We will be demonstrating how conduction happens. Conduction was defined earlier as a charging process where two surfaces must be in contact with each other so that electrons or electric charges in that sense or electrons will jump from one material to another when two surfaces are in contact. Now, if I'm going to rub this balloon to the sweater, what will happen? The balloon collects or collects the electric charges, the electrons from the sweater. And because two surfaces were in contact with each other. Now, if I'm going to let go of my cursor, and notice that the balloon is away from the sweater, and I'm going to let go of it, what will happen? Alright, the balloon is attracted to the sweater. What is that? Okay. Now, what can we say about the charge of the material? Right? From this one, all of them are neutrally charged objects. So if I'm going to rub the balloon to the sweater, it collects the electrons present. And what happens? What's the net charge of the material? The balloon contains more electrons than before. So that makes our balloon a negatively charged object because there are more electrons present. Now, on the other hand, notice that the balloon is attracted to the sweater. And why is that? Because there are no electrons present, thus making it positively charged because there are more protons in the sweater rather than having electrons. Because the electrons were transferred to the balloon. Now, what does this imply? What does this imply? It only shows that when two opposite charges are in contact with each other, they are attracted to one another. Now, notice this is how conduction happens. But what about induction? So induction doesn't need a direct contact. Now this object is a negatively charged object, and this wall here is a neutrally charged object. So what would happen when we place this object, the balloon, near the wall? And please take note or please observe the charges present. Okay, what happens to the negative charges? The negative charges are being repelled. Right? They do not attract one another because negative charges repels one another. So in this case, the negative charges are being repositioned. This is by induction. The negative charges are repositioned. That is what we call polarization. It's being polarized. So there it is, and it is attracted only to the positive charges. But what happens? Okay, what happens to the negative charges? It repositions themselves. The positive charges stays. Right? The negative charges are being repositioned. So what would happen if there are two balloons? Okay? There are two balloons. Now, a neutrally charged object, what will happen here? So by me, I'm going to collect. Okay. So the same process happens. The same process is happening, right? Very good. So that is by means of conduction and induction. Any questions? If there are none, then that's great. To furtherly understand the process of charging, we need to also to understand the different properties of electric charges. So there are three properties of electric charges. First, charges are quantized, charges can be separated, and charges are conserved. So what do we mean by quantize, separate, and conserve? So quantize, by means of quantization, we can say that charges can be counted individually. We can identify the as a physical property where we can identify the the, uh, the integer or the integer number, or what how do we call that? We can identify how many electric charges are present in the system. It's quantized. And we can separate charges. We can isolate charges from positive charge to a negative charge. So if there is a group or a system of electric charges, we can separate the negatively charged particles from the positively charged particles. And of course, charges are always conserved because charges are innate with the matter of are innate in the system or in the object, because every object has or contains subatomic particles, and these subatomic particles has their own charges. They have positive charges in the manner of a proton, and a negative charge in the manner of the electron. So charges are conserved; they are not created by someone. It is, and you cannot destroy it. If you disintegrate an object, the charges remain. Okay, the charges remain because it is made out of matter. It has an innate electric charge. So again, the three properties of electric charges are quantized, charges can be separated, and also they are conserved. So having these different properties of electric charges, having these electric charges and its different properties, we can say or we can define electricity as an interaction of electric charges. In a sense, electricity in a sense is an interaction of electric charges, but static electricity is the interaction of electric charges when they are at rest. Now, it doesn't mean that we are doing conduction, we are um, the the electric charges are repositioning themselves. It doesn't mean that they are moving already. They are only showing what? They are only showing the repulsion and attraction by means of electrostatic force present, but they do not move. Right? They do not move. They do not travel from one point to another. They are still at rest. Right? So that is static electricity. Now, there are three main uh, there are three main things that we need to talk about in static electricity. For the first part, right? For the first part, we will be talking about Coulomb's law, electric field, and electric flux. So Coulomb's law is also known as electrostatic force, the force present when two objects are or two particles or charged objects and charged particles are in contact with each other, how much force is being exerted by one another. Electric field is the amount or the strength of the force present in a certain area. And electric flux is also um, similar with electric field. Are there any questions so far with the properties of electric charges? If there are no more questions, then great. If you have questions, please comment down. Now, before we begin our discussion in electrostatic force, I would like you to identify first what would happen to these charged particles. Now, there are three pictures, and they vary in the they vary in their charge. So in the first picture, we have what? We have two positive charges and a negative charge. The second picture, there are two negative charges, and the third picture, there are two positive charges. Now, what happens in picture number one? Will the charges attract with each other, or will they repel each other? Now, notice that in number one, there are two charges present, positive charges rather, and a single negative charge. Now, what would happen to the two positive charges? They will what? If we go back into our basic lesson in magnetism, or in yes, in magnetism, when we were in grade 8, what happens? The two charges, two poles, two identical poles will what? Will repel with each other, and different poles will attract each other. The same is true with electric charges, because that particular law in magnetism comes from electricity. Now, it's what we call the law of attraction and repulsion. Now, according to the law of attraction and repulsion, is that when two identical charges are in contact with each other, they will repel one another. And when two different charges are in contact with each other, they will attract one another. So that's when two identical objects will attract and two different charges will come into another, they will repel. So what would happen to these charges here in number one? Of course, the two positive charges will repel one another, but these two are attracted to the negative charge. So basically, number one is our what? These charges will repel. Number two, there are two negative charges, so they are the same charges, so they will attract one another. Number three, also there are two different. They are two. No, they are not different. They are the same positive charges. So what would happen to them? They will also repel one another. So we have been talking about attraction and repulsion here. Now, what is the connection of this attraction and repulsion to our lesson? Now, in attraction and repulsion, we can just say that two identical objects or two identical charges or charged particles will repel one another, and two different charges will attract one another. But the question is, by how much? Yeah. By what is the strength of the attraction? What is the strength of the repulsion? And that strength will be answered by Coulomb's law. or electrostatic force. Now, according to Coulomb's law, what is Coulomb's law? Coulomb's law is a mathematical relationship of two forces between of the force, no, between two charged particles. And this relationship determines the amount and the direction of the attraction and repulsion. So ano ba ibig sabihin na what do we mean by attraction and what do we mean by repulsion? Attraction is that charges comes together. Repulsion is that they are separating with one another. So by how much are they attracted to one another and how much are they repelled by one another? Now the loss of electric charges is evident. Is the evidence of a force between two charges at rest. Now, even though they are at rest, but they are different, they will be what will happen to them? They will attract or repel one another. Now, based on the different experiments that is being conducted by physicists long time ago, it shows that the electrostatic force exerted by a charge Q to a charge Q, okay, between the charge is represented by letter Q. So there are two charges. We can say that's Q sub 2 and Q sub 1. Now the electrostatic force between these two charges Q tells us that the force of charge 1 points towards charge 2 if the charges have the opposite signs. Okay? So if the two charges Q1 and Q2 have the opposite signs or they have different charges, the force is pointing towards each other. But if the two charges has the same nature, or if they are both positive or both negative, then these two charges, the force applied is away from each other if they have like signs. Now, Coulomb's law is defined mathematically as a force, as an equation of force. We have here F sub E that would say F is a force and would show us that this is electrostatic force. Okay? It's equal to the absolute values of two charges, okay, Q1 and Q2. Now, Coulomb's law is always between two charges or two charged objects. Okay? So, in a proportion, the electrostatic force is directly proportional to the product of two charges, and is inversely proportional with the square of the distance between these two charges. Now, to make this an equation, we need to introduce a constant, and this is what we call the Coulomb's constant. It is written as small letter k. Now, the electrostatic force is dependent on the amount of electric charges present in the system of the product of the two electric charges in the system with respect to the distance that separates the two charges. And of course, we have the Coulomb's law that would allow us to be the constant. So this is how Coulomb's law is being written. Now, the K is a constant value. It is equal to 9 times 10 to the positive 9. So later on, we will see how it is being written. It's 9 times 10. That's the approximation. 9 times 10 to the positive 9 Newton meter square per Coulomb square. Some books is writing it as 8.98 times 10 to the 9 Newton meter square per Coulomb square. Okay. Now let's put this equation into a test. Okay. But before putting the equation into a test, we need to identify also. We need to understand the different physical quantities and the symbols present in the equation. Now, as I have mentioned a while ago, that F in the equation is electrostatic force. The measure of force, of course, if it's a measure of force, the unit that we're going to use is Newton. And R is the distance, which is in meters. Charge is represented by Q, which has a unit of Coulomb. And of course, a Coulomb's constant is K, small letter k, which is equal to Newton 8.9 times 10 to the 9 or 9 times 10 to the 9 Newton meter square per Coulomb square. This is not seconds, this is Coulomb. Letter C, capital C. So do not confuse with the capital C and the small letter c, because the capital C, that will tell us that it is a speed of light. Capital C, the meaning, that's the unit of electric charge. So Newton meter square per Coulomb square. So these are the different variables in the Coulomb's law equation. Now, it's time to put the equation into a test. Now, there are two identically charged particles, and these particles are separated by a distance of 1 meter. Now, these charges are repelled by one another with a force of 1 Newton. What is the magnitude of the charge? So we can say that these two charged particles are repelling with one another. So meaning, if they are repelling with one another, they have the same charge. Yes, they have the same signs. So, but we do not know if it's positive or negative, and that's our job to find out right now. Now, what are the given variables present? We have the distance of 1 meter and a force of 1 Newton. Now we are trying to look for the magnitude of the charge. So how do we do that? Of course, we're going to use our Coulomb's law equation. F is equal to K times Q all over R square. And this is it. Right? So F is equal to K times the absolute value of Q1 times Q2 divided by R square. Now, since there are two Q's here, and these two are unknown, but we know that they are just the same because they are identical. So meaning they have the same amount, they have the same magnitude, right? So we can write it here, Q1 and Q2, and we need to transform the equation, this equation, into this equation. And how do we do that? How do we do that? It is by multiplying both sides with r. What happens if we multiply both sides with r square? R square will what? What will happen to r square? It will cancel out. So let me show you how do we derive this one. Here, F, F is equal K. Let me repeat again. F is equal K times Q1, Q2 all over R squared. So we need to transform the equation into Q, wherein Q is our variable that we need to find. So how do we do that? Is we need to multiply both sides by r. I want Q, these two Q's, to remain on this side of the equation, and I want this K and R to be transferred here. And what we can do is that we can equalize the equation by multiplying R square both sides. If we multiply R square both sides, okay, that would give us, this will cancel out because R square divided by R square, that's equal to 1, right? So, and then we divide both sides by k. If we divide both sides by k, that would give us this one. Then this one will cancel out because that's also equal to 1. So that this not approximation, this equalization will give us Q1, Q2 is equal to F R square all over K. And remember that these two Q's are identical and they have what? They have the same magnitude. So the same magnitude, so we can just write this as Q square. Yes? We can just write it as Q square. Two identical, two the same variables. So that's how we equalize our equation. So deriving the equation to find the magnitude of our electric charge. Now, going back, now we have this equation. We have this equation. So what we can do here is that we can substitute all of the given variables. Remember that F is equal to 1 Newton, R is equal to 1 meter, and K is equal to 8.9 times 10 to the 9. So what we can do here is that we can just substitute and go with the flow of the equation. So we have F1 times 1. So we have here 1 Newton times the quantity of 1 meter square all over K. So if we simplify this one, we will have, this is just the same. I did a boo-boo here. This should be 1 meter square, but so please don't mind the parentheses here. This should be 1 Newton meter square all over 8.9. Okay. And then, of course, the quotient of 1 Newton meter square divided by 8.9 times 10 to the 9 will give us 1.1 times 10 to the negative 10 Coulomb square. Remember, this is still the square of Coulomb. So this is Coulomb square, and this is Q square. So the product of these two is, or the product is equal to 1.1 times 10 to the negative 10. But we are looking for the magnitude of a single charge since they are identical. So what we can do is, we know that the product, or the value of Q is equal to the square root of Q squared. Okay? How do we do that? Is what? We get the square root of the values in both sides of the equation. So if we get the square root of Q squared, that will give us Q. Right? That will give us Q, and the square root of 1.1 times 10 to the negative 10, that will give us 1.1 times 10 to the negative 5. And the square root of C squared is C. So the value of our individual charge is 1.1 times 10 to the negative 5 coulombs. So that's the magnitude of our electric charge. Hence, we can recheck this one if we substitute 1.1 with Q. So if we substitute 1.1 with Q, that will give us 1 Newton along the way. Okay. Any other questions? We have questions for this one? If there are questions, please comment down your questions in the comment section. Now, before I part you for electrostatic force, I'm going to give you one problem to solve. Let me read the problem. What is the net force experienced by Q2 if Q1 and Q2 is 1 meter apart, and Q2 and Q3 is 2 meters apart, considering that the particles are all protons. Alright? Now, so there are three charges present. Okay? And both charges are separated by a certain distance. Now, what are you going to find is what is the total force experienced by Q2? If Q1 and Q2 are separated with 1 meter by 1 meter, and Q2 and Q3 is separated by 2 meters. Considering all of the charges or the particles are protons. So I have here an illustration. I have here an illustration that would depict the separation of the charges. So this is Q1 and Q2, they are separated by 1 meter, and Q2 and Q3, they are separated by 2 meters. So what amount of force? Of course, they are all protons, so they are repulsive. They are repelled by one another. So by what force, what is the total amount of force is experienced by Q2? That's for you to find out. Thank you very much for watching, joining this session in weekly physics on electricity, particularly on Coulomb's law and introduction to physics, then going to Coulomb's law. See you next session.